So in this next quantum mechanics lecture, we're going to expand on the idea of particle models by talking about a 2D box. So previously we discussed it in one dimension. We're going to add a dimension and find out a couple of implications of that. And then we're going to also discuss the particle on a ring, which is a one-dimensional model, but there's a slight change to it that actually adds some interesting effects to it. Because we're going to then find out, well, so what? What are these models going to tell us? We'll have one more model after that that will require an entire lecture. And then after that, we can basically justify the shape and size of most atomic and therefore molecular orbitals, which is pretty good. So, quick recap of what we've done previously. We've looked at the particle in a box model, and when we do this, we mean the particle is free. That means there is no potential constraining it. There is no force or energy acting on it to try and slow it down or speed it up. It's just free to go about wherever. So that means it's governed by a sine or cosine wave. So that is the equation that will describe a free wave traveling through space. There are a few reasons why it's sine and cosine, but we're not going to touch upon them too much here. We just need to know that they are solutions to the Schrödinger equation, so a sine and cosine wave it is. And this wave squared, this is the main interpretation of it. Squaring it gives us the probability of finding the particle at a particular point. So wherever the value of the wave is highest, the particle is most likely to be found there. We're going to skip over the interpretation of what that is. That's for arguments later. So the end result is that we can build up various waves that fit inside the box. We can fit one sort of half a cycle in, a whole cycle, 1.5, or when n equals 4, we fit a couple of whole cycles in there. So what you can see is that we are increasing the number of times it crosses the x-axis. These are known as nodes. And also, the wavelength decreases. So the wavelength of the higher quantum numbers is decreasing. And if you remember back to the equations brought up in physical spectroscopy, well, the shorter the wavelength, the higher the energy. So now what happens if we add a new dimension? We're trying to put this into a square box rather than a wire or a line. We're going to end up with some slightly different constraints. The function must be 0 at the edges. Previously we said it only needs to be 0 at 2 points, but actually all along these lines, these edges here, you can never find the particle. You can never find it outside. The function must hit 0 there. And it must still also satisfy every other constraint we put on wave functions. It must be continuous, it's got to be a finite value, etc., etc. And it must obviously be a solution to the Schrödinger equation. So this could be a little bit complicated if you're not used to functions in multiple dimensions, but thankfully we can split it into two components. We can look at the x and y directions separately and see what happens. So if we look at, say, the x direction, well, we could just fit our normal sine wave in there. Sine n pi L of x. We covered that one previously. And that fits, that constrains. It means that at each of those points it will be 0. We can add in the next level up. Again, it will work. And in the y direction, well, we can do the same thing. We could add in another sine wave. It's exactly as before, in pi over L x. And we could keep ramping up the quantum number there. And to get that to work in both directions at the same time, we would need to multiply those together. So we can get a final equation that looks a little bit bigger than you might be used to of this. But it is just two particles in a box, here in the x direction, and then the y direction, multiplied by each other. So that is a two-dimensional wave function. This will plot the probability of finding a particle if we dropped it into this box and allowed it to travel freely, but not in a way that it could ever leave. We would be able to get the probability of finding it by squaring that. So what do the functions look like? If you're not used to reading contour graphs, maybe go look that up. But it just means that if we're starting at 0 here, as we move across these contour lines, the probability increases, so that the maximum probability here is in the middle. And that should make some sense, because if you tilted this box on its side and looked along it, you would get a mound sort of shape. It would be that sine wave we saw earlier. And if you tipped it the other way and looked along, you would again get a sine wave. That makes some sense. But those are for the quantum numbers when they're both 1. What happens if we escalate one up? We change 1 to 2. Well, the wave looks slightly different. In this case, with contour graphs, we can only really jump to different colours to try and say which is positive and which is negative. But if we say that the orange is positive over here, then if we tilted it back and looked along it, we'd see a sine wave that looks like that. If we tilted it the other way, we'd see a sine wave that looks like that. And of course, if you were to physically orientate that, you would see the bottom half of it. But that's just the same thing, multiplied by a negative number, because this side is negative. But there's nothing special about escalating the x direction by 1. We could actually do it to the y direction, and we get the exact same thing tilted 90 degrees around. We've twisted it around a little bit. So if we look along this line, there we go, we've got our normal sine wave there. Here we've got it again. So where this is positive, it multiplies by this positive one. Here we go, there's the maximum value. Here it's negative, so here negative. But what happens if we increase both quantum numbers to 2? Well, we get this sort of pattern going on here. So we have a sine wave that looks like that, and here, both are positive. They're going to form positive there. Here's negative, and a negative multiplied by a negative gets you to a positive, and then negatives multiplied by positives get you negative numbers. So those blue quadrants there are negative. But remember, we need to square that to get probability, so all of that would become a positive real number in the end. And that pattern continues. We can increase each of these quantum numbers by 1, 2, however we like. So let's compare the energies. I'm not going to derive the energy for that. That's on a separate video because it's just takes a while. It's not infinitely more complicated. It's just a bit more involved. In one dimension, the energy is governed by that equation there, n squared h squared over 2m, where m is the mass of the particle and the length of the box. If we do the same derivation in 2 dimensions, we get a very, very similar formula, except here we have n squared plus n squared in the x and y directions. And that's an interesting idea because we could have 1 is equal to 1 and the other is equal to 2. And 1 squared plus 2 squared is 5. But there's nothing special about putting in that direction. That area, we could do 1 and 2. 2 squared plus 1 squared is equal to 5. So in both of those cases, the energy will come out as exactly the same. So we're getting 2 combinations of quantum numbers that give us the exact same energy. We'll get on to what that means shortly. So here we're going to move on to a particle in a ring, and a ring is slightly simpler because we're only dealing with one dimension. All we're doing is how far does something travel around the ring, or what's its angle around the ring, so it's one dimension. But the boundary conditions are periodic, so where we've got a 1D box in one direction, we can actually wrap it around on itself and it becomes periodic, which means at this point, or indeed any point, whatever is happening to the function when you plug in 0 must be the same as when you add 360 degrees or add 2 pi to it, or in fact when you add 720 degrees, 940, etc., or adding 2 pi, 4 pi. anytime you add that whole circle around the function, it must come back to the same thing. Not only the same value, but also the same slope. If you're going up at 0, you must be going up 360 degrees around it. And that adds an interesting constraint when we try to draw it out. So if we kind of imagine the x direction being how far along we've traveled around the ring, and this being 0, and the equivalent of 360 degrees, we try a sine function like we've got previously. Well, this doesn't work. The sine function wants to continue coming down here, but actually, because it's periodic, we're looking at that point again, and there's a contradiction here. This point, when it wraps around on itself, is no longer continuous. That doesn't satisfy. However, that wave function does. We go up, we go down, we go up again, because at the start, we're still going up. That will continue around and loop perfectly. And finally, and we'll get onto this, we could also get this. Previously, we had to be 0 at the edges of the box, but on a ring, there are no edges. There are no edges on this box. It loops around on itself. All it needs to be is the same gradient and the same value, so it is perfectly acceptable to have a wave function that's flat. That still satisfies all the criteria. Go back over them and satisfy yourself that that is a good wave function based on the criteria previously discussed, because that is a wave function. So the equations that govern this are here. They're a little bit more involved. We're not going to do too much maths on them, but in short, we could have a sine or a cosine function for this. That's really useful to know. In fact, let's go back and draw that. Previously, we said in a particle in a 1D box, that couldn't happen because it is 1 here when we're supposed to be 0. That's no longer a constraint because it's still going to have to, but it can still come down. So that loops around nicely, so the cosine function fits. More conveniently for maths and physics, we want to express that as an exponential function because e to the ix is a sine and cosine wave mixed together. We're not going to cover the maths of that in depth. That's more for the physicists and the mathematicians that are interested in it. Chemists, we can hand wave our way around it. We don't really care too much. And the kinetic energy operator simply involves the radius of the ring. There is a reason for that. Part of the derivation involves angular momentum and moment of inertia, which we've covered in physical spectroscopy. So a couple of ramifications of the ring, like why is this interesting? Well, the quantum number in this case I've labeled as L. Sometimes you see it as M, but I don't want to get confused with maths, so I'm using L. That can take 0, and that is what that flat, perfectly smooth, straight wave function was. Or it can be plus or minus integers. +1, -1, +2, -2. Well, there are 2 quantum numbers for each absolute value. And one interpretation of that, and a fairly good interpretation, is that plus values mean going one way around the ring, and minus values mean going around the other way. So that's really interesting. We can produce the same energy in the same wave function, but with either a plus or a minus going backwards. And that interpretation leads to, what does 0 mean? It means the particle isn't traveling around the ring at all. The particle can be found anywhere on the ring without actually traveling around it. It doesn't have angular momentum associated with it, but it can still travel around the ring. Welcome to Shout at the Physicist about how to interpret your way around that. It's just what the math says and what the evidence suggests as well. So interesting interpretations to that model, at least. So this leads to what are the point of introducing these two models, and it gets us degeneracy. So these models introduce this concept. You may have come across it before. We talked about it in spectroscopy. It basically means that there are multiple states or wave functions that produce the same energy, the same observable. We shove those states into the Schrodinger equation, we generate the same energy back. So you couldn't really tell the difference between the states just by measuring them. It's a really interesting idea. And there are implications here in some of the statistical mechanics and the entropy. We get onto that next term. Some parts of this have already been covered a little bit in spectroscopy, but leave it to statistical thermodynamics before we tackle it in too much depth. So one of the interesting things about degeneracy is that we can actually then break it. So in the 2D particle in a box, this formula for energy only holds true if the two lengths are the same. So if the box is square, we get this degeneracy out here. So we could have multiple combinations of n that produce the same. We could have 1 and 2, or 2 and 1. Both of those produce the same energy. Not so if we make the box a different length. We can reduce one energy level and increase the other one, because the formula then becomes this. So it's quite clear here, if these numbers are different, then which of these is 1 and which one of them is 2 becomes important. So we don't get degenerate states here. In fact, you can kind of sketch them out and realize, well, if that was the wave function one way, the wavelength is about that long. And if we increased it the other direction, the wavelength would be a little shorter, it would be higher in energy. So those are not going to be the same energy. We can prove it either visually and look at the wavelengths or from the formula. So let's recap. If the degeneracy is broken, one energy level becomes lower, the other one raised up. And that means we can actually get some energy back by breaking degeneracy. So there is a little bit of a force, a bit of a pressure that can be exerted by breaking degeneracy. And we have seen this before in chemistry because of Jahn-Teller distortion. So we actually do see this in molecules, not necessarily in the model quantum systems, but in real models we do see it. So here we have an octahedral. We probably say that this is delta oct. These two molecular orbitals, d orbitals, are degenerate. They have exactly the same energy. This is a perfect octahedron, and if you solve what the energies of those orbitals should be in that octahedron, they come out the same. Same for the three at the bottom, they come out the same as well. But if we were to stretch and elongate that molecule a little bit, that degeneracy is broken. We get one is slightly lower than the other is raised up, and the three at the bottom also separate as well. So if we have electrons in here to give it energy, we actually get some energy back by lengthening the molecule and lowering the energy of that orbital. So there are real effects to breaking degeneracy that can be seen in molecules. Right, so we are introducing new models. These are the 2D box and the ring, because we get degeneracy from them. In the box, we can rotate things by 90 degrees. We get degenerate states. In the ring, we can do it clockwise or we can go anti-clockwise. They'd be degenerate states. And these are states of functions that have the same energy or observable value. So that brings us to the end of these models. Next, we're going to cover a slightly more complicated one because we're finally going to bring in potential energy again.